Okay, welcome to the linear algebra class, and my name is Hong Jun Kim. And let me briefly introduce the outline of the class. So here is the updated version of the syllabus. So let me briefly explain this. So how we will, you know, study through the online class. So okay, 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 so the course is linear algebra with lab session 2. And this course is a online class meeting via Zoom on every Tuesdays and Thursdays from 10:30 to 11:45. So, but the exam will be held in person, okay, in Hana Science Hall room basement 207. I will I will let you know when we have the exams. So the online lectures will be given the real time, but the exams will be held in person. So you take the offline exam. Okay. Please remember this. I will announce that in more detail just before the exam. Okay, my name is Hong Jun Kim. And if you have any questions or suggestions, complaints, anything, please email me. So email is preferred way to communicate in this class. And linear algebra is a fundamental area of mathematics, and that studies systems of linear equations and properties of matrices. And this linear algebra has become an indispensable tool in many branches of sciences, from pure mathematics to economics or engineering or in data science. The course will be taught in 2 semesters, and in this semester, the course will introduce some basic concepts and theorems of linear algebra, including systems of linear equations, solutions, vector spaces, and their transformations and determinants, and so on. So we will study those concepts so that at the end, after you take the course, you should be able to formulate and solve systems of linear equations and understand elementary facts about vector spaces, which is important. And you should be able to perform some linear transformations and identify certain properties. So that is the course objective. The textbook will be the linear algebra written by Friedberg, Insel, and Spence, written by 3 people. The edition does not, you know, is not that doesn't matter. So you may have global or international edition if you purchased it in Korea, or you might have a US edition. Either is fine. Okay, so any edition will be fine. And if you need any reference, I usually recommend the book by Gilbert Strong, The Linear Algebra and Its Applications. So it explains many concepts, okay? And it provides many intuitive explanations, okay? Some people prefer those explanations, intuitive explanations, but some people prefer some mathematical calculation stuff. So if you want some calculation-oriented textbook, you can search the Google for linear algebra and the same title, linear algebra and its applications, written by Lay. And Anton's linear algebra textbook is quite easy. Usually the book by Lay or Anton is taught in just 1 semester. So those two are very simple. So those will be nice textbooks or references. And here's the course outline. We will cover first the 4 chapters in this spring semester. Hopefully, my plan is to cover first the 2 chapters before the midterm so that I can evaluate your knowledge regarding those 2 chapters in the midterm. And then I want to consider the the next 2 chapters, chapter 3 and chapter 4, in the final exam. So we will have the midterm. I plan to have the exam on April 22nd. That is Tuesday. And then I want to have the final exam on June 16th. That is also Tuesday. So for these 2 exams, you need to come to the classroom I mentioned. So we have the in-person, offline exam. So you shouldn't forget. I will announce that before the exam one more time. But anyway, please remember that we will have the exam, okay, offline, in person. So please remember that. And the course is designed for students from a various majors, from mathematics to engineering or life sciences, economics, statistics, and so on. Okay. And I don't think any prerequisite is required for the course. So probably if you took the high school algebra, that would be sufficient, I guess. Okay. Okay, the grading, that is important, right? So there will be 2 exams, as I said. The midterm will be given on April 22nd, and the final exam will be given on June 16th. As I said, this exam will be held in person in Hana Science Hall, room B207, I guess. Okay, and each exam is worth 45 points. And attendance is essential because missing lectures will hinder your ability to keep up. So I assigned 10 points for the attendance. And your grade will be determined through the absolute evaluation. There might be a chance for, curve at the end of the semester, but anyway, at this point, what I can tell you is that your grade will be determined through the absolute evaluation, and if your score is 95 or above, you get A plus. Between 90 and 94, you get A, and so on. Regarding the attendance will be checked automatically through LMS and Zoom. Okay, and if you attend more than 90 of the class time, that will be regarded as attended. Okay. But if you miss more than 10%, say if you watch only between 50 to 90%, then that will be marked as a tardy. If you watch less than 50% of the class time, that will be regarded as absence. And if you make 3 tardies, that will be counted as 1 absence. Okay, so please be careful. So you need to watch at least 90% of our class. Our class consists of 1 hour, 15 minutes, 75 minutes. Okay. So the 90% of 75 minutes must, okay, you need to watch more than that. The system will check automatically. Okay, so, and everything will be recorded. So if you leave early or if you join late, then if you do not watch the lecture less more than 90%, then it will be marked as a tardy. So please be careful. Now, regarding these 10 points for the attendance, if you make fewer than 3 absences, you get 10 points. But if you make 3 to 6 absences, you will get 8 points. If you make more than 6 absences, you get only 5 points. But please note that we have the official university policy which assigns an F grade to any student who misses more than, actually, who misses 1/3 or more of total class sessions. That's the school policy. So if you miss more than 1/3 of the classes, you get an F automatically. So please be careful. Okay, I cannot help with this one. Now, as I said, the attendance is checked automatically through LMS and Zoom, and we have many students. And I cannot check the attendance manually. So I will rely on the system. Okay. And at the end, I will run the program to check the attendance automatically. Anyway, I will talk about that in a moment. Okay. Now, if you have any physical, psychological, medical, or learning disability that may impact your coursework, please contact me. Please email me. Okay. I will determine with you what accommodations are necessary and appropriate. And of course, all the information and documentation you provide will be confidential and will be destroyed right after I check those information. I will destroy those documentation. Okay. So if you have any such situation, please email me. So that's the one simple announcement for our class. And then before we start today's class, let me explain a little bit more on our online class. So this is the announcement. You can, so if you log into the LMS website, the mylms.korea.ac.kr, you will see this announcement. Okay, so first thing, okay, please do this. Please change your Zoom display name, okay? Before you join the class, please change your Zoom display name to your student ID number. So for example, if your name is, say, Gil Dong Hong, and your student ID is, say, 123456, please change your display name to this one. Please do not use your real name or any combination of ID with your names. Okay, please avoid this. Okay, please use your student ID number as your display name so that I can check the attendance. And once you log into the LMS website, please click Weekly Learning from the left-hand side, this one. If you click this, then you will see something like this. Okay, the environment, the window may be slightly different from yours. Now, the link for each day is formatted as month dot day. So 3.3 is the Zoom link for today's class, March 3rd. And 3.5 is the Zoom link for March 5th. If you click, say, today's link, then there will be a link. So this link will be named as a start a video meeting. So if you click, please click this one to join our class. If you just copy the link and then log in through Zoom directly, attendance is not possible. Attendance checking is not possible when you join the Zoom link like this, using this one. So please do not use this. Please click this start a video meeting. So say on Thursday, if you click 3.5, you will see a start a video meeting. So please click this one, okay, to join our class. And if you click the board, there will be some syllabus I just showed, and the lecture notes can be found, can be downloaded from there. So you can use this board to download the material. Okay. And as I said, if you have so So I still have some students who didn't change the display name, but starting next time, please change the display name to your student ID number so that I can check the attendance automatically. And as I said, if you have any questions, please let me know through the email. Okay, then let's consider the first section of this chapter 1. So, okay, we will consider something called a vector, and I will define a vector or vectors in a moment. But before I define the vector, in many other fields of science, say in physics, they have some definition of a vector. Okay, so they say any entity having the magnitude and direction is called a vector. So that was the definition used in physics. And to represent those concepts using some, first images or intuitive explanation, people may consider the set of arrows to describe the vectors. So we want to consider some set of arrows to describe vectors. And in this set of arrows, we regard two vectors are the same if they have the same direction and same magnitude. And here, the magnitude of an arrow is represented by the length of an arrow. So if, in other words, when you consider two arrows having the same length and the same direction, then we say we regard them as the same, okay, equal arrows or equal vectors. Okay, so given these two vectors, x and y, we say they are equal. We say they are the same if they have the same direction and the same length or magnitude. In this set of arrows, we want to define the sum of two vectors. So given two vectors, x and y vectors, if I want to consider their summation, what you need to do is you move these two arrows so that they initiate from the same point. Okay, this x prime and x are the same because they have the same direction and the length, and y prime are the same. So when two vectors x prime and y prime, you introduce two vectors x and y such that x and x prime are the same and y prime are the same, and x and y both originate from the one point, say P. Now, given these two vectors x and y, the sum x plus y is defined by the following. You, given this x and y, you introduce a parallelogram like this dotted line. This parallelogram, this dotted line has the diagonal. Okay, first of all, this parallelogram is defined with x and y as two sides, two adjacent sides. Given this parallelogram, you have only one diagonal. So that diagonal will be regarded, that will be defined, that will be, okay, that is defined by the sum of x and y, or the sum of x prime and y prime. So that's how we define the sum of two arrows in the set of arrows. And this method is called parallelogram law for vector addition. Okay. There are several ways to visualize this or explain these concepts. So please read this material yourself. So anyway, that's how we define the addition of two arrows. And sometimes we want to multiply certain number to an arrow. So given x arrow, I want to multiply some number, say t, to x. I want to define this t times x when x arrow is given. So one way is this. Depending on the sign of the arrow, the number t, if t is positive, then we define tx by the arrow having the same direction as x, but whose length is t times the original length of x vector. Okay, so when t is positive, if then you consider the arrow in the same direction whose length is magnified, okay, by a factor of t. Now, if t is negative, then you consider the same arrow, but you change the direction to the opposite. So when t is negative, the length of the arrow is scaled by the absolute value of t, okay, and then direction is changed to the opposite direction. So for example, given x, this will be negative 1 times x, or this is 2 times x. So x and 2x have the same directions, but the only difference is the length. The length of 2x is just doubled from that of x. In case of negative 1 times x, negative 1 is the negative value, so you change the direction to the opposite direction, and the absolute value of negative 1 is 1, so the length is unchanged. So in this way, you consider some multiplication by some number. Okay, and that multiplication by a number is called scalar multiplication. And here scalar means some real numbers. Okay, I will define this scalar in a moment, but anyway, that's what means in this set of arrows. So in the set of arrows, we could think of the addition of two arrows, or we could multiply some number to an arrow. Okay. Then under these definitions of addition and scalar multiplication, the set of arrows will satisfy these properties. So for any two arrows, x and y, x plus y and y plus x will be always the same. When three arrows are given, x, y, and z, the sum of x plus y plus z will be the same as x plus y plus z. In other words, x plus y and y plus x are the same. So that means it is commutative. And the sum of three vectors will be the same regardless of the order of addition. So that is means associative. And for any x, there will be some arrow denoted by 0 such that x plus 0 equals x vector. In other words, so here this 0 vector will be an arrow with length 0. Okay? And for each x, we can find one vector y such that x plus y becomes that vector 0. And if I multiply number 1 to any vector x, the vector is not changed. And for any real numbers a and b, these relations is satisfied. And for any number a and b and vectors x and y, these equations are satisfied. So this is what happens with the set of arrows. So we could identify those properties. You can easily prove these properties yourself. Okay, then so that was explained in section 1. Now in section 2, okay, then in section 2 in mathematics, what we want to do is okay, I want to go back to this, and then we want to consider some set satisfying these properties. Okay, so as I said, if I consider the set of arrows, that set of arrows will satisfy these 8 properties. So in mathematics, we want to find some other sets satisfying those 8 properties. Okay, so that's what we want to study in the next section. But before we consider these examples, I want to redefine the scalar. So in mathematics, when I say a field F, when I say a field, it is a set. It is a set of something on which we can define two operations, plus, addition, and multiplication. Okay, so that means if I given this, so if F is representing this set, and if F is a field, then in this field F, I can consider any pairs x and y. Okay, as I said, on which two operations, plus, addition, and multiplications are defined, so that for each pair, we can define x plus y and x dot y, and in addition, this x plus y and x dot y are included in the set F. Okay, in other words, okay, so x plus y and x dot y are included in F. In addition, this addition and multiplication satisfy some properties. First of all, a plus b and b plus a are the same. and A dot B and B dot A are the same. In other words, addition and multiplication are commutative. So the order of appearance does not matter. And when I consider the addition of three elements and the multiplication of three numbers, so A plus B plus C will be the same as A plus B plus C, and A plus B multiplied by C will be the same as A times B dot C. Okay. And there exists some number 0 in F such that 0 plus A equals A, and there is another number 1 such that 1 times A equals A. And for each element in A, there exists some number C such that A plus C equals 0. And for any number B in F, okay, as if that number is not 0, we can always find some number D such that B dot D equals 1. And they satisfy this distributive law. Okay, so the x plus 1, so if your set satisfies these properties, so then the set will be called a field. Okay, so field is a set. First of all, the x plus y and x dot y must be some numbers in F. Okay, they should mean, okay, so x plus y and x dot y, they must be included in F. In addition, they must satisfy these 5 conditions. In that case, we say this set is a field. And given this field, x plus y is sometimes called the sum of two numbers, and x dot y is called the product. And the numbers, this is called 0, and this is called 1. And this 0 is the identity element for addition, and 1 is the identity element for multiplication. And the C satisfying this relation, this C is called the additive inverse for A, and the D such that B dot D equals to 1 is called multiplicative inverse for B. So as an example, the set of real numbers is a field. Okay? And the set of rational numbers is a smaller field. So in mathematics, we will consider many different examples of fields, but in our class, we will consider only two fields, two types of fields. One is the set of real numbers. And if I do not specify any other condition regarding the field, I mean the set of real numbers. So when I just simply say a field or scalar, that means that number is a real number. Okay? So when I say a scalar, it will represent a real number. Sometimes we can extend this real number system to complex numbers. So complex number is an expression of this form. Here, A and B are real numbers, and I is a symbol such that I squared becomes -1. So I is that imaginary number, okay? And if you consider numbers of this form, then this Z will be called a complex number. And given this complex number Z defined by A plus BI, A is called the real part and B is called the imaginary part. And given two complex numbers, a plus bi and c plus di, their sum, if I call them by z and w, their sum is defined by this. In other words, you need to add real parts and imaginary parts to define a new complex number. And their product is defined by this. Okay? So if I consider such complex numbers, then the set of complex numbers will be another field. You can easily prove this. Okay, so in our class, in our class, I will some we will consider only two sets of fields. One is the set of real numbers, and the other is the set of complex numbers. And in most cases, I will usually assume that the scalar fields are real numbers. But in some cases, I need to extend the number system to complex numbers. Okay, and in that case, I will let you know. So anyway, so when I say a scalar field, I will consider only two possible examples. One is the set of real numbers, which is denoted by capital R, and the other one is the set of complex numbers, which is denoted by C. And the numbers in those fields will be called a scalar. Okay, so when I say a scalar, if the scalar field is R, then scalar means a real number. When I say a scalar for a complex numbers, then in that case, the scalar is a complex number. Now, given this field, okay, from now on, when I say a vector space, it is a set, okay, on which two operations are defined. Okay, and for each pair x and y, similarly to the set of arrows, we can define x plus y and some multiple between the number in a scalar field and one element in V. Okay, this scalar multiple is defined. So the sum addition of two elements in F in V, and for any element in a field, and given any element A in field F and any element X in V, we can define their multiplication somehow. And this x plus y and a times x must be included in V. So in other words, we say the addition is closed in V, and scalar multiplication is also closed in V. So the addition and scalar multiplication, those are closed in V space. And in addition, it satisfies several properties. First of all, x plus y and y plus x are the same. In other words, this addition is commutative. Given three elements x, y, and z, they satisfy this associative rule. So in other words, you may add x and y first, and then you can add z later, or you can add y and z first, and then you can add x later. In either order, the results will be the same. And there will be some element denoted by 0, such that x plus 0 equals x for any x. And for that 0, okay, for this 0, for each element x, we can find one y such that x plus y becomes this is 0. And then for any element x, if you multiply the real number 1 to x, you get x. And for any numbers in the field f, and for any number element x in V, a times bx will be the same as a times b times x. That means you can multiply two numbers in f first, and then you can multiply their product to x. Or you can multiply one of these two numbers to x first, and then you can multiply the remaining one at the end. In either way, you get the same result. And for any pairs x and y in V, and for any number in the field f, a times x plus y will be the same as ax plus ay. And for any two numbers a and b in f, a plus b times x will be the same as ax plus bx. If these are, if these properties are all satisfied, then this set is called a vector space. That's how we define a vector space in our class. So as you realize, the set of arrows will be one example of a vector space. Given a vector space, the numbers of the field f will be called scalars, and the elements of the vector space will be called vectors. Okay, so in our class, when I say a vector, then that means there should be a vector space for the first time. Okay, so you must have a vector space first, and then the elements of a vector space will be called the vectors. So if I consider the example of the set of arrows, then any arrow in the set will be called a vector. An object of this form, so the collection of n numbers, that will be called an n-tuple. Okay? And if I choose this a1, a2 up to an from this field f, then these n numbers, this is called an n-tuple with the entries from f, and the elements a1, a2, these are called entries or components of this n-tuple. And we say two n-tuples are equal if the corresponding entries are equal. So, okay. So if I consider, say, a1, a2, a3, and if that equals to, say, 1, 2, 3 uh, in R3 space, then a1 is 1, a2 is 2, and a3 will be 3. That's what this equality implies, okay, between two n-tuples in Fn space. Okay, now let me show you some examples of vector space and some sets which are not the vector spaces. So please be careful, okay? And if you have any questions, please email me. Okay, so first of all, given any f, given any field, if I consider the set of all n-tuples with entries from this field f, that will be denoted by Fn, and this is definitely a vector space. So what does this imply? So Fn, what is the meaning of this? So it is the collection of the n-tuples, a1 up to an. Here, a1 up to an are numbers in this field f. Okay. So if I consider two such vectors, say u and v, with a1 up to an as the components of u and b1 up to bn as the components of v, then we can define their sum like this. Okay. Then and if this f is the set of real numbers, then this R3 will be a vector space over R. If f is a complex number, and say if I consider a pair of complex numbers, okay, then we can consider C2 space. C2 space is another vector space. So it consists of vectors with two complex numbers as the components. Okay. So these are some simple examples of vector spaces which we will consider quite often. So R3, or sometimes Rn, will be the collection of n tuples of real numbers. Sometimes we will consider Cn space, that will be the collection of n tuples of complex numbers. So those are some trivial examples of vector spaces. And in our class, usually vectors in Fn are represented by column vectors rather than row vectors. Okay, but so sometimes the authors may use row vectors, but anyway, that's what. So when people say vectors in the ordinary sense, that they usually imply the column vectors. Now, on m by n matrix with entries from a field F is a rectangular array of this form. So this is the collection of mn numbers. Okay. And here, this horizontal collection of the numbers is called a row. So this A11 up to A1n will be called the first row, and next horizontal group will be called a second row, and this will be called the mth row. So row 1, row 2 up to row m may be considered. So those horizontal grouping will define a row. Sometimes we need to consider the group of entries in vertical way. So if I consider this group of entries, that will be called the first column. And next group of these entries in vertical way is called a second column, and so on. So in this example, in this slide, the given matrix has m rows and n columns. Then we say this matrix is an m by n matrix. So this m by n specifies the size of the matrix. It just counts the number of rows and the number of columns. So m is the number of rows of the given matrix, and n is the number of columns of the given matrix. Okay. And here a sub, as I said, a sub ij, or a sub ij is representing the entry in the ith row jth column. So this is the ij entry of the matrix. That means it is the entry on the ith row and jth column. Given this matrix, sometimes we can define a matrix with which is filled with only zeros, then that is called the zero matrix. So for example, 0, 0, 0, 0, 0, 0 is a 2 by 3 zero matrix. 0, 0, 0, 0 are 2 by 2 zero matrix. Some people, some authors use zeros of 2 by 3 or 0 by 2 by 2 to represent those zero matrices. But in our class, we will just use just 0 to represent those zero matrices. And the size can be understood from the context. And when the matrix has the same number of rows and columns. So in other words, if you consider an n by n matrix, then such a matrix is called a square matrix. So in that case, so that means the number of rows and the number of columns are equal. In that case, we say that matrix is a square matrix, and we say two matrices are equal if, first of all, their sizes are equal, and then corresponding entries are all the same. Okay, so we say two matrices are equal, okay, if they have the same size and the corresponding entries are equal. In that case, we say two matrices are equal. Okay, so I just explained, let me go back to this. So given this matrix, we have this new concept. Okay, I just explained how to consider an m by n matrix. Given this m by n matrix, if I have two such matrices, we say they are equal if they have the same number of rows and the same number of columns and the corresponding entries are the same. And given those set of m by n matrices, so given this set of m by n matrices, suppose that I define the sum of two matrices by this and scalar multiplication by this. In other words, given two such m by n matrices, the sum of two matrices is defined by adding the corresponding numbers. And when I consider the scalar multiple, you multiply the scalar to each entry of the matrix. So for example, given these two matrices, the sum will define the matrix of the same size whose entry is defined by adding two corresponding entries. So 2 plus minus 5 will give you minus 3, and 0 plus minus 2 will be minus 2, and so on. So by adding the corresponding numbers, we can define some product, and that product is the sum of two matrices. When I have a matrix and one number, their scalar multiple is defined by multiplying this number to each entry of the matrix. So if I define the sum of addition, matrix addition, and scalar multiplication by this, then the set of matrices will define a vector space. You can easily check this. So that vector space will be denoted by this. So m sub, okay, uppercase M sub m by n. So here, so the subscript m by n denotes the size of each matrix in the set. So this m sub m by n means this is the collection of all m by n matrices, and f inside the parenthesis represents the scalar field. So if you want to consider the set of, say, 2 by 3 matrices over the real numbers, that set will be denoted by this. If you consider 2 by 2 matrices over complex numbers, then that is denoted by this. So those will be all vector spaces. Okay? You can check this yourself. Now, here's another example. Here, S denotes any non-empty set. Any non-empty set, say the closed interval from 0 to 1, for example. So something like this. So any non-empty set. And F be any field. So, for example, the set of real numbers. In that case, when I use this symbol, that will be the set of all functions with domain S to codomain F. So that will be the collection of all the mappings from S to F. So that is what this symbol implies. So that is the collection of all the functions from domain S to codomain F. So this is the collection of all those functions from S to F. Now, given this set, we say two functions are equal if the images of F and G are equal for every value in the domain. And given this set, and given two functions, F and G, we define their sum by the sum of image values. And scalar multiple is defined in a similar way. So if I define the addition of two functions and scalar multiplication by this, then you can show that this set will be a vector space. Now, please note that, okay, let me go back to the examples and then explain this more time. So here, in example 1, I consider the set of real numbers and the set of complex numbers. Okay, so in other words, we considered Fn space. In Fn space, we know so the sum and scalar multiple, and you can easily show that this Fn will be a vector space. Okay, so everything depends on how you define the addition of two elements and scalar multiplication within the set. Okay, given this Fn space, which is one vector space, any element in the set will be called a vector. So for example, in R3 space, 3 minus 2, 0 is one vector. Minus 1, 1, 4 is another vector. C2 is another vector space. And in C2 space, 1 plus I and 2 is one vector there. This is another vector there. So that Fn is one vector space which you will see quite often throughout the semester. Now, based on Fn, we could extend to the set of matrices. So here, in this set of matrices, we just learn how to define the equality between two vectors, and we learn how to add and perform scalar multiplication. So under this ordinary definition of addition of two matrices and scalar multiplication, the set of m by n matrices will define another vector space. So in that space, this is one vector. This is another vector. Okay, so in chapter 1, I considered vectors, okay, in very small scope. So in that set, we considered the set of arrows. That was the arrows were vectors there in that space. But here, in this example, in example 1, column vectors are the vectors considered in Fn space. In example 2, if I have this new definition of if I have this definition of addition and scalar multiplication, this matrix will be called a vector, and this m sub m by n will define a vector space. So everything depends on the addition, the definition of the addition of elements and scalar multiplication. So in example 3, I consider the set of functions with domain S and codomain F. So I'm just considering the collection of all the functions from S to F. Like, say, when say S is, say, real number R, and if this is F or so, then, for example, say fx defined by x squared, gx defined by x plus 1, and then f plus g of x will be x squared plus x plus 1. That's how we define the sum of two vectors. We can double the f by multiplying 2 to x squared. So that's how we define the scalar multiplication. So if I define the addition and scalar multiplication by this, then the set of all the functions will define a vector space. Polynomial is a function of this form, and that is another function, one function, right? So, and okay, so if a polynomial may be considered, I guess you probably know what a polynomial is. Now, given this polynomial with coefficients chosen from some scalar field f, so for example, you may consider, say, polynomial with the real coefficients, then an up to a naught will be all the real numbers. So given this polynomial, okay, we want to consider the set of all the polynomials. The set of all the polynomials. If they have, given this f, if a sub n is not 0, and if this n is the largest power in x, then we call this n as the degree of a polynomial. So given this polynomial f, this n is the degree. So as an example, if I consider the f of x defined by x squared plus 1, then this is a second order polynomial, second degree polynomial, and gx defined by x cubed will be the third degree or third order polynomial. Okay? Then, given two polynomials, if given two polynomials, we say two polynomials are equal if they have the same degrees and if all the corresponding coefficients are equal, then we say two polynomials are equal. Actually, that's how you define the equality between two polynomials in elementary school days. right? Now, now, when F is a field containing infinitely many scalars, we usually regard a polynomial with coefficients from F as a function from F to F. So if I consider this polynomial, then this is a function from F to F, right? Now, now, suppose that I have two polynomials f and g defined by this, where the coefficients are all chosen from certain field f, say real numbers or complex numbers. Okay? Then how can we add f and g? Say if I have x squared plus x plus 1, and if gx is defined by x squared minus x plus 2, how do we define f and g? We just add the corresponding coefficients. So 2x squared plus 0 plus 3. So that is a sum of two polynomials, right? But what if f and h is given, where h is, say, x plus 1 and g is, then how can I add f and h? Intuitively, if I have x squared x plus 1, so f is a second degree polynomial and h is the first degree polynomial, then what is the sum of f and h? The sum, how did you learn in elementary school days? If you add these two polynomials, you get x squared plus 2x plus 2. Why do I get x squared? Because in case of h of x, I don't have any second order term because h is the first degree polynomial. So I temporarily add second order term with zero coefficient, right? And then you add corresponding numbers, right? So if f is an nth degree polynomial and if g is mth degree polynomial, and if m is less than n, then what usually you do is you add some terms with zero coefficients, as I did in h. So you temporarily add 0x squared. It doesn't change the value of the function. And then you just add corresponding coefficients, right? That's how you get this f plus h. So if you use this trick to define the addition of two polynomials, and when you multiply any number to f, when you do this, you multiply that number to each coefficient to define scalar multiplication. So if you use these two ways, if you define this addition and scalar multiplication by these two tricks, then the set of polynomials will define a vector space. And this set of polynomials will be denoted by P of f in our textbook. Okay, so we have the Fn space, the set of column vectors, and we have the set of m by n matrices, and we now have the set of polynomials. In high school days, probably you learn a sequence, right? So for example, given a1 is 1, a2 is 1 half, and a3 is 1 half squared, and a4 is 1 half cubed. If I have such a sequence of numbers, then this notation is just a mapping which maps 1 to 1, 2 to 1 half, 3 to 1 half squared, 4 to 1/2 cubed, and so on. So sequence may be regarded as a function which maps these positive integers 1, 2, 3, 4 to some numbers 1, 1/2, 1/2 squared, and so on. Okay. So instead of a sub n, we may use this notation sigma of n to denote the number. So that means we use sigma 1 to denote the a sub 1, then a sub 2 is denoted by sigma 2, and that is denoted by sigma 3 and sigma 4 and so on. So this sequence, one sequence will generate a one function. If I define another sequence, say b1 is 1, b2 is 0, b3 is 1, b4 is 0, and so on, then I have another function, say sigma, say mu1, mu2, mu3, mu4, like this. So in this way, I can define another function. Then previously I just explained, we just observed that the sum of two functions, sigma plus the mu of n, is defined by sigma of n plus the mu of n, which is a sub n plus the b sub n. And if I define the c times, or t times sigma of n is defined by t times sigma of n, which means t times a sub n. So if I define the addition and scalar multiplication like this, then you can also show that the set of these sequences will define another vector space. Now, so far, we just observed the examples of vector spaces. Now, let me consider the following. Suppose that S denotes the set of pair of real numbers. Set of a pair of real numbers. Now, if I redefine the addition of two pairs of real numbers by this, please note that I'm using minus for the second term, and the scalar multiple is not changed. So this is not the R2 space. In R2 space, A1, A2 in R2 plus B1, B2 in R2 is generating A1 plus the B1 and A2 plus the B2. So if I have this definition of addition, then that will define a vector space. But if I modify the definition of addition, then we have a problem. For example, under this definition of addition, 1 and 1 plus 1 and 1 will become 1 and 1 plus 2 and 1 will be 3 and 0. I'm sorry. 2 and 2. Just a second. So it will be 1 and minus 1. But 2 and 2 plus 1 and 1 will be 3 and 1. So commutative law is not satisfied. And you can easily check that the second and eighth property are not satisfied as well. So if I modify the definition of addition, then this set of pair of real numbers does not define a vector space. Anyway, let's call it a day here, and then let me continue on Thursday. And if you have any questions, please email me. Okay? Thank you for listening and see you on Thursday.